Hi everybody, Dr. Pingle here with the applied part of the lecture. We're going to talk a little bit about interpolation methods for point to raster conversions. Hopefully you've watched the lecture slides already, and we'll show you a little bit how to do that in ARC. So I've got ArcGIS loaded here. The first thing I want to do is bring in some point data. Remember that most of what we're going to be working with here is going to be point data that's relatively sparse. So when we looked at other data sets, we saw that they were fairly dense. So the Chicago crime data set that we looked at, there were a lot of points in the space. In contrast, I'm going to add in some temperature data here. So just go to the desktop. And this is just a CSV file. It's good practice to sort of work with these kinds of things. A lot of the data that you can download on the web is not going to be in shapefile format, but CSV files, especially when it's a relatively simple data set. So this is an example of what that data set looks like. We just have a longitude, a latitude, and then a temperature observation. So we brought these things in here. So here's the data table right here. So there's your longitude, latitude, and temperature. Now keep in mind that this is just a table, so what we need to do is we need to bring these things, we need to display the XY data, we need to map it. So our X field is going to be longitude, our Y field latitude. We're not going to have a Z field. Always define this if you can, so the coordinate system of the input, right now it's set to unknown coordinate system. It has no idea what those X and Y values are. And so we're going to declare this as WGS 84. Okay, so you can already sort of make out the outline of the United States here, but we can bring in a base map. Actually, before I do that, I want to set a projection. I suppose it doesn't really matter, so we'll bring the base map in here, just a light gray canvas. That'll just take a second to come in. So here are our values. Now, in the lecture slides, what I had done is gone in here and defined a projection. So I don't remember exactly which one I used, but probably I went to continental, North America, and then you can pick any of these, probably something like USA Albers equal area or Lambert conformal conic. It doesn't really matter. This is just for visualization. So that'll take a second to reproject both the base layer and the point data. Here we go. Always get these warnings. You can turn those warnings off. I almost never do. I think it's a nice reminder, letting you know kind of what's going on behind the scenes. If you get really sick of it, you can definitely turn those off. So while we're moving around in here, you'll notice that there's this pause. It sort of takes a little while before it redraws all of this stuff. So ordinarily, if you're making a map, you'd want to make sure that you were in something suitable. This is a really nice projection if we're just looking at the lower 48 here. But I'm going to change the property back, and we're just going to use a web Mercator. And the reason I want to do this is I want to leave the base map on, and this is going to make it so that it's a little bit more responsive. It won't have to reproject this all the time. Okay, so we have all of this point data, and one of the things that I would suggest is that if you're going to be working with XY data that you brought in from a CSV file, much of the time you can get away with that, and ARC should handle that fine as long as you've declared your coordinate system. But one of the things I like to do is just to export that back out again. You could export it back out as a geodatabase, or in this case, I'm just going to bring it out as a shapefile. So we're just going to go to the desktop in this temporary GIS folder I had made, and we'll just call this temperature.shape. So the reason I like to do this is just to make sure that it's working in as native of an ARC format as possible. Again, should work just fine if you're working with just a CSV, but sometimes ARC can be a little temperamental. I'm going to go into the properties here and change the symbolization to what I did in the lecture. In this case, I think I had used quantities, graduated colors. We're going to use the temperature field to do it, and we're going to use temperature as the color ramp. I'm going to set the classes to 32, but I'm also going to go in here and change this. Natural breaks is not really appropriate for data like this. It's great to find sort of the natural breaks in the system, but in this case, I've got its temperature. What I'd really rather do is do something more like equal frequency, right? So that the categories are evenly spaced, or equal interval, I'm sorry. So we'll use equal interval to kind of smooth these out, and we'll get something that looks like this. Now, what I had done to make this a little bit more visible is to change the symbology so that those are a little bit larger. So you can come into here and change the properties for all of the symbols. And instead of 4, you could crank that up to 12 or something like that so that they're all a bit larger. Okay, so now we can kind of clearly see the pattern. Warmer temperatures in the south, cooler temperatures in the north, generally speaking. So the question is, how do we create a raster from this that sort of gives us the temperature all over the United States? Well, one of the things that we can do, we've got a number of different interpolation tools. So let's start with IDW. So for whatever reason, it's not inverse distance weighting, it's IDW. There are a couple of different variants of this. I use the one in Spatial Analyst. And so what we're going to be doing here is we're going to be guessing the value, based on nearby observations. So the first thing that I had done, you're going to declare your input point features as temperature. Your Z value field, this is going to be the field that you're interpolating, the field that you want to estimate. So in this case, I want to use temperature. Output raster, same as always. This is where you're going to spit out that image. So we'll call this temp IDW, and I'm just going to put a 1 here. And the reason I want to do that is, and we want to change we really want to make sure that you are specifying the output value. You'll notice that it's a floating point raster, which means that that this can have decimals in it. So it doesn't really matter what you're bringing in. It's going to be spitting out a floating point raster. Output cell size, this is going to change. This is going to control the resolution of the image. You can set this to whatever you want. This is going to be the same as your input units. So in this case, my input units, we declared this as WGS84, so the unit is a degree. So this is 0.091 degrees is going to be the resolution of each cell. But you could set that to whatever you want. It's going to infer this automatically based on your spatial layout. This is the power. So this is going to tell you how it's going to weight those observations. If you set it to 1, then the weight of the observation is going to be proportional to the inverse of the distance. So if you're 5 units away, the weight is going to be 1/5. And you can change this value. 2 is the default, and that's pretty typical. You can see that most reasonable results are going to be between 0.5 and 3. I would suggest kind of leaving this alone in the short run. This piece is kind of important. So this is a search radius. So you can define a search radius and say, I want you to use all observations within, in this case, this would be 0.5 degree, all of the observations within 1 degree, and so on. You can also have it be variable and say, I want you to use the 12 closest observations, and optionally I can set a maximum distance and say, okay, use the 12 closest observations, but don't use anything farther than 1 degree away. If you're very far away, you're going to use whatever, up to 12, but not exceeding 12. You can also include barrier polyline features. So if you have things that are definitely going to discontinuities in the surface, for instance, that might change those values, then you can include those as well. If you're doing things like estimating a terrain surface, and you know that you have a cliff somewhere, a cliff face, then you can use that cliff face. You can draw that explicitly in, and it won't smoothly interpolate through that feature. So we're going to leave this alone for now. I'm going to erase that maximum distance. We're just going to use the 12 closest points. So this is sort of a default here. So IDW doesn't really take all that long to run, which is very handy. Here we go. So what we've done here is we've interpolated the surface. Now you can see that the color scheme here is really more terrain based. A lot of people would use these kind of interpolation schemes to, for instance, take contour lines and generate a raster, or take point observations of an elevation, maybe gathered from GPS, and create a raster of the elevation, a DEM. So in this case, we can change this. So that's why the default is sort of this terrain pattern. But you can change the symbology just like anything else. So we're going to, again, choose temperature. And to make this match up a little bit better, what I want to do is I'm actually going to change this to stretched. Same idea here. Oops. We're going to select temperature. And instead of so here we can describe how that color map lines up with the values. You can change these things around. We're just going to choose minimum and maximum. So this is going to be exactly the same essentially as our point layer. So you can see that it goes from -7.39 all the way up to 22.79. So we'll hit apply and hit OK. And now what you should see, and we do see, that our point values, which are drawn over the top, are basically exactly the same as what's going on underneath. So if we uncheck our point values, you can see that even in these places right here, we actually did have a value that was purple. So I think the interpolated surface actually does match pretty well. Now, if you zoom in very closely, you'll start to see that some of the it's not terrifically smooth kind of in this region. You can see that an IDW kind of does the best with what it has. Here we have 2 points, for instance, one relatively cold, one just a little bit warmer. And the system has a bit of a hard time figuring that out. It does it, and it does it fairly well. But you can see that we have these relatively different values. We've got a really cold spot here in the middle of kind of a relatively warmer spot. You also see, if you zoom in here, sort of the large number of kind of discontinuities here that you can see in the color pattern. If we were to do things like draw contour lines on top of this, those contour lines wouldn't really look all that good. Let's zoom out. I wanted to show you one more thing with IDW. So in the lecture, we had talked about nearest neighbor interpolation. So here, if we again set our temperature, our output cell size is going to be the same. But we're just going to use 1 point. So use the closest point to determine that value. Here, in this case, it won't really matter what the power is because the weight is essentially always going to be to the nearest neighbor. And let's save this. We'll call this IDW2. And we'll hit OK. So what we've done here is we've done this interpolation, but instead of I'm just going to import the other scheme here so that they match up. Okay, so essentially what we've got here is these Voronoi or Thiessen polygons rasterized, and these are neighborhoods. So we're assigning the weight of that whole section of this part of the raster to whatever the closest station data is. So this tends to produce some fairly odd pieces here. So you wouldn't often use it in practice. You can see that along this boundary zone, we get some really peculiar values where you're exactly the same distance away from one to the other. So kind of an odd way to draw this, but it's important to kind of be at least a little familiar with nearest neighbor interpolation, even though you might not use it all that much. One of the ones that you would probably use is natural neighbor interpolation. So this is also in the Spatial Analyst, and comparatively, this is a lot simpler. This is a lot simpler dialog box. So if we use temperature as our input, we'll spit this out here. Temp natural neighbor. Let's save it as a TIFF. We'll leave the output cell size default again. We're kind of using this 250 value to figure it out. So we'll hit OK. And what we've got here is a very different pattern, in a lot of ways smoother Let's change this to stretched, and we're going to import the same one. So first of all, you'll notice that we're not making any guesses outside of the range of the data, so that's important. So there's no extrapolation, whereas we do have some minor extrapolation going on. It's not a very good one. Some minor extrapolation kind of going on out here. These values in the extrapolated range, where we're really outside of our observed data, are often not very reliable estimates. So we'll turn that back on. And one of the things that we can do is to kind of slide between both of these. So I don't think I have this toolbox turned on, but it's one of my favorites. So just pausing here for a second. So what I'm looking for is the effects toolbox. It's been a while since I used that, so I needed to look that up again. So here we go, the effects toolbox, and it's this swipe tool. And what that is going to let me do is kind of add and subtract these different pieces. What I want to add and subtract, here we go. So here, this is letting me sort of swipe and compare my natural neighbor interpolation, which is what you see when you were on top here, and the IDW, our first. So in comparison, you can see that the natural neighbor really smooths things out in this particular area. You can see these weird discontinuities kind of go away when you get there. So it's just a generally sort of a better product overall. So the other one that we looked at, so this is in the 3D analyst, the spatial analyst toolbox, and the spline-based tools in there. We're not going to focus on that one, but I did want to do kriging as kind of the final. Kriging, and then we'll look at a trend surface actually. So we'll use kriging again, similar sort of a thing. We're just going to be doing an interpolation. Temperature layer based on temperature. We'll spit this thing out as kriging1.tiff. Some of this is pretty similar. So semi-variogram model is going to be describing the assumptions that we're making about how things fall off with distance, how related phenomena are as we get further apart. But a lot of this stuff should look pretty familiar. This is a lot of what we saw in the IDW box. So output cell size, same as usual. We can set a search radius, we can set the number of points. We'll just leave these things at the default settings for now, although when you're actually doing an interpolation, you may well want to tinker with those a little bit. So we'll import the same layer. Okay, so this is our kriged surface. We can turn on our original data points here. You can see that these mostly align well, but we do have some differences. If we use our swipe tool again, and what we're swiping on and off is going to be temperature this time. You know, these values do more or less correspond, but you can see that this blue one over here is probably you know, it's close, but probably the kriged surface has smoothed that out a little bit, and you get a few other instances where that is true throughout the map. So remember that kriging does not guarantee that the point observations or that the raster surface that we're estimating doesn't go through, which means we could have some differences between what we measured and what we estimate at the end. There's another one kind of at this purple area here is getting washed out a little bit. There's just too much temperature difference going on in that spot, and the algorithm is sort of smoothing that out. The last one that I wanted to look at was the trend surface. So this is really handy. Similar sort of beginning here, but the key pieces here, the key piece here is really the polynomial order. Linear versus logistic regression. Logistic is used if you're trying to predict sort of a yes or no binary value. Most of the time you're likely to be using a linear regression. The polynomial order is what's really going to make the difference. So this depends on what you're doing. You're probably going to want to use a value of 1, 2, or 3, depending on what you're doing. The default is 1, which is a linear regression, which means we're essentially, if you think back to the lecture slides, we're essentially putting these together using straight lines to estimate. Whereas a second order or third order polynomial is going to allow for this sort of curvature. Now remember, what you're doing here is you're fitting a surface. So a polynomial order of 1 is going to fit a plane to the data, and that could be sort of misaligned, but it's always going to be straight, meaning it could dip to the lower right, for instance. Polynomial order 2 is going to let that surface be curved. So it really depends on what you're trying to show. So I'm going to set it to 2 for now. And we get a very different kind of a raster here. And again, the emphasis is not on prediction so much as to extract an overall pattern of the data. So the overall pattern of the data is something like this. You can see that it doesn't fit our observations. It does, but only sort of very generally. But what we do have is sort of this idea that we get colder temperatures as you move northward. You get slightly warmer temperatures in the northwest than you do in the northeast. But what's really cool is that you get this continental effect, where it's colder in the interior of the continent than it is sort of at the coasts. So the trend surface sort of helps us visually ID and express that general pattern, not so much about predicting particular values. So that's your quick introduction to raster interpolation. We could do things like use the raster calculator to subtract one of these layers for another to sort of explore the differences, but we'll leave that for another time. So hopefully you found this interesting. Point to raster conversions are really very common. We've looked extensively at this example, which is sort of a meteorological example, trying to figure out, okay, based on a few surface observations, could we predict temperature across the whole of the United States? But that kind of a problem is fairly typical. Species frequency counts was one example. Groundwater level estimation were two examples that we talked about in lecture. So lots of different applications for this. So definitely try this out. And thanks for listening, and we'll catch you next time.